Okay, so it is time to review Unit 10, specifically LeChatelier. I'm also going to walk you through the puzzle piece assignment that you had, but first let's review some content. So first, a quick review before we get to the questions. Might help a little bit. Okay, so first we talked about collision theory. So in order for reaction to occur, we obviously need collisions. So if you want baking soda and vinegar to react, you can't just have them in separate containers, right? You actually have to mix the baking soda with the vinegar together. So we need collisions, but not just any old collisions. We need effective collisions. So what are the two things required for effective collisions? Well, we need the right amount of energy, and later we'll talk about it again, but that's equal to or greater than the activation energy. And we need the correct orientation. That means they gotta line up right. So remember we talked about building with Legos. If you're pressing the wrong sides together, no matter how hard you press, no matter how much energy you apply, if they don't line up right, no reaction. So we need the right energy and the right orientation, okay? Okay, now we're gonna talk about reaction rates. So rate just means the speed of the reaction. How quickly is it occurring? How quickly are we going from reactants to products? It is affected by 4 key factors. First of all, temperature, sometimes called energy, sometimes called heat. So if we increase the temperature, we're going to increase the rate of the reaction. If we decrease temperature, we're going to decrease the rate of the reaction. We have surface area. So surface area, remember, means just breaking it into tiny pieces. So if we increase the surface area, that means itty bitty pieces. So the reaction rate increases. So if we want something to happen faster, we use smaller pieces. And if we decrease the surface area, meaning use a big piece, then the reaction occurs more slowly. Then concentration. Concentration means how much of the stuff we have in there. So for example, if you wanted to make Kool-Aid more concentrated, you'd add more sugar. So if you want to make the concentration higher, you're going to add more of the stuff, okay? So it's adding more of the reactant, okay? So concentration is the amount of stuff that's in there. So more concentrated Kool-Aid has more sugar in the same amount of water, okay? So concentration, increased rate. And then adding a catalyst. Adding a catalyst makes the reaction occur faster because it provides an alternate pathway with a lower activation energy. It increases reaction rate. All right, the properties of equilibrium. First, it's dynamic. That means literally stuff is happening. It's not just sitting there like this. Okay, stuff is happening. Reactants are being turned into products. Products are being turned into reactants. Stuff is literally happening. It's reversible, so kind of like what I just said. We have a forward reaction and a reverse reaction. The forward reaction is reactants to products, and the reverse reaction is products back to reactants. And our rates are equal, so the forward reaction and the reverse reaction are occurring at an equal rate. Whatever that rate is, every equilibrium is different. And the concentrations are constant. So the amount of products and the amount of reactants stays the same, but some is getting turned back into reactants, some is getting made into products, but because the rates are equal, the concentrations are constant. So concentrations are constant, rates are equal, it's dynamic, and the reaction has to be reversible. If it's not reversible, you can't get to equilibrium. And the final thing, it has to be in a closed system. So that means put a lid on it. Okay, put a stopper, put a lid, close the container. Because if you're letting stuff escape or stuff enter the system, it's not going to reach equilibrium. So what are the two main types of equilibrium? Well, we can have phase equilibrium. So that means like between the same substance, but at different phases, like water as a liquid and water as a gas, or water as a solid and water as a liquid, or any other substance, as long as we're talking same substance, two different phases. Or we can have a solution equilibrium, and that only applies if it's saturated, which we'll learn more about later. But that means that some of it is dissolving and some of it is recrystallizing or solidifying, and those rates are equal. Remember, equilibrium, always talking about equal rates. All right, so LeChatelier is response to stress. Now, we as people don't respond perfectly to stress, but equilibrium responds perfectly, beautifully, always responds in a way to relieve the stress perfectly. It can respond to temperature, energy, heat, changing those, changes in concentration, changes in pressure or volume, okay? So for LeChatelier's principle, when we increase concentration, the system shifts away from that. If we decrease concentration, the system shifts toward that. For energy or temperature, it responds the same way, and you'll see when I later run through some examples. Okay, pressure or volume is only going to affect gases. So when we squish it into a little volume, increase the pressure, we want to go toward the side that has less gas molecules. All right, and potential energy diagrams. So we have here, this is an endothermic reaction. Reactants start low, products end high. So that means energy was absorbed in this process, endothermic. For exothermic, reactants start high, products end low. There was energy released, exothermic. Okay, what else can we tell? This net energy released or absorbed is also called delta H, or the heat of reaction. We also have activation energy. Activation energy always goes from where you start to the tip top, the activated complex. So from where you start, reactants to the top. From where you start, reactants to the top. So up here is the activated complex. And then we can have a look at the forward and the reverse reaction. So the forward reaction goes like this. Starts here, goes up to the activated complex, and then goes back down, and then our products are over here. When it's the reverse reaction, we start here, go up, still to the activated complex, and then our products would be over here on this side, okay? If the forward reaction like this one is exothermic, the reverse reaction is endothermic. Okay? Okay, when we add a catalyst, we start the same, we end the same. The only thing that changes is we create an alternate pathway with a lower activation energy. So you can see up here was our original pathway. Down here is the pathway with a catalyst. So we start the same, we end the same. We just have a pathway that has a lower activation energy. So this activated complex is lower. Okay, so that is how potential energy looks different with a catalyst. You have to remember, ends the same, starts the same. Okay, it's just like a shortcut. Like, come on, let me take you on a shortcut. All right, that's a catalyst. That's it, just going on a shortcut. Explain in terms of collision theory. So already see this in terms of, that means my answer has to talk about collision theory. How would I talk about collision theory? Use the word collide or use the word collisions. So let's see. Explain in terms of collision theory why the rate of a chemical reaction increases with an increase in temperature. Well, when I increase temperature, that means an increase in kinetic energy, right? Because temperature is kinetic energy. We just talked about that. If I increase kinetic energy, then my particles are moving faster, okay? If the particles are moving faster, when they hit each other, when they collide, okay, so there's a collision right here, they're going to hit with more energy. So, in terms of collision theory, why the rate of a chemical reaction increases with an increase in temperature. Because with an increase in temperature, the particles collide with more energy, right? So the particles collide with more energy. Excuse my mouse handwriting. Which means the collision is more likely to be effective. So I increase the number of collisions, but even more importantly, I increase the number of collisions that have enough energy. Okay. All right, given this reaction at equilibrium, which change will result in a decrease in the amount of NO? So let's look. I want the amount of NO to decrease. All right. Well, if I want the amount of NO to decrease, which way do I want my reaction to go? Well, let's see. If I'm decreasing NO, I'd be using it up, right? In order to use it up, my reaction would have to be going this way, to the left. So, which one of these things will make my reaction go this way? So let's switch colors. What if I decrease N2? Well, if I decrease the concentration of something, it's going to move that way, toward that same side. Remember these right here, the arrows, that's like the divider. So I have this side and I have this side, okay? And on either side of the divider. So if I decrease something, the reaction is going to shift toward that same side. So this one so far, this looks pretty good. Like this looks like my answer. Let's check this one. Decrease the pressure. Well, remember, pressure only affects gases, but it affects total gas molecules. So let's make a box for reactant side and product side. And inside the box, let's put a number of molecules. So how many molecules of N2 do I have? Look for the coefficient. I have 1 N2. And how many molecules of O2 do I have? Well, I have 1. So I have a total of 2 molecules. I have 1 N2 and 1 O2. Now let's look on the product side. I only have one thing, and the coefficient is a 2. So I have 2 molecules of NO. So the number of molecules is the same on both sides. So changing the pressure does nothing. Okay? All right, so let me swap colors here. What if I increase the concentration of O2? Well, if I increase O2, anytime we increase concentration, it shifts toward the other side. Well, that's the opposite way I wanted it to go, so that's wrong. And increasing temperature. Well, what thing in this reaction represents temperature? That's energy. If I increase energy, anytime you increase something, it's going to shift toward the other side, so that's going the wrong way. So I was right in the beginning. This is the correct answer. Okay, so remember, I have a bunch of reading, so what is my strategy? Skip to the question. So here's the question, here's what I'm going to start reading. Explain in terms of collision theory. So I'm going to underline this because why? That is what it says in terms of. So again, that means I need to talk about collide or collision. Why increasing the concentration of Cl2 gas increases the concentration of OCl negative aqueous in this equilibrium system. So let's find Cl2 gas, and it says I was increasing it. Well, what happens when I increase the concentration of something? Find where the arrow is. It's going to switch to the other side. So it's going to go this way. So that means I'm going to start using up this extra Cl2, but I'm also going to use up some of this, and now I switch sides. So I'm going to make more of this, I'm going to make more of this, and I'm going to make more of this. So why does increasing the concentration of Cl2 gas increase the concentration of OCl negative? Because the equilibrium, right, shifts which way? Shifts to right. And there are, but see, I have to talk about collision theory, right? And there are more collisions, right? And there are more collisions. So I could have a perfectly wonderful answer. And if I don't talk about collisions, my answer is wrong. So my mouse typing is subpar at best. So in terms of collision theory, why increasing the concentration increases the concentration of OCl negative? Because there are more collisions, right? Collision theory, there are more collisions. Anytime you increase the concentration of something, you're going to end up with more collisions. So more collisions is the key. All right, again, right here, skip all of this, go to the question. Here's the question. State one change in reaction conditions other than adding a catalyst. That means I can't say catalyst. That would cause the rate of this reaction to increase. Well, what did I tell you? Say increase temperature. Those are the two things that you should remember. How can I increase rate? Increase temperature or add a catalyst. I can't say catalyst because it says other than adding a catalyst. So there's your answer, okay? What are your other options? Well, I do have something that's a solid. So I could say increase the surface area, okay? And I have gases, so I could say increase pressure, right? But always what I recommend is to say increase temperature to increase rate or add a catalyst. But since I can't say catalyst, the answer should be increase temperature. All right, let's look here. This is just kind of a review. What happens during this reaction? So look, I started with F2 together. I added energy in, and then I ended up with F and F, so separated. So first of all, energy is on this side. Here's my arrow. So it is on the reactant side. This is product side. When it is on the reactant side, energy is being put in. So that is absorbed. So I know it has to be absorbed. So that means this is wrong and this is wrong. So now what is happening to the bond? Am I breaking it or am I forming it? Well, I started with F2 stuck together and ended with F plus F. So I broke a bond. All right, so let's look at this one. Which statement, again, we're going to skip all reading, right? Go straight to the question. Which statement describes the concentration of the two gases in this system? So concentration, I'm being asked to describe concentration. Look at this. It says it is at equilibrium. So it's helpful in this case to look back up here for a second. So what do you remember about concentrations at equilibrium? The concentrations must be constant. So this is the right answer. A reaction is most likely to occur when reactant particles collide. They need to collide effectively, right? So it's an effective collision. And that effective collision needs two things: energy and orientation. So the right energy and the right orientation. All right, given this reaction, it says the concentration of A can be increased by. So I want to increase A. How can I increase A? Well, I would have to shift the equilibrium in this direction, which would make more A and make more B, and use this up, use up the AB, and use up the heat. So the reaction would shift this way to make more A. So how could I make that happen? Well, let's just look, before I even look at my answers down here, let's look at the equation. So how could I make the reaction shift this way? Well, I could increase this, shifts away. I could increase this, it shifts away. Or I could decrease this, shifts away. I don't really want to change A because that's what I'm trying to change in the whole scheme of things, right? So what is true? Did I lower the temperature? Negative. Did I increase AB? Ooh, that looks right. What about this? Adding a catalyst. Remember, catalyst does not affect equilibrium, so that's a wrong answer. Catalyst speeds up forward and speeds up reverse. Increasing B. Well, I didn't increase B, I decreased it. So my answer is this. So if trying all these things before I even look down here at the answers, that was super helpful. All right, so now let's look at this one. Remember, we're skipping straight to the question. State one stress other than adding or removing NO2 or N2O4 that would increase the amount of a dark brown gas? Okay, well now I need a little bit more information. So let's go back up to this and say, oh, here's a dark brown gas. Which one is the dark brown gas? NO2. So I want to, let me switch colors. I want to increase the amount of the dark brown gas. So I want to increase the amount of NO2. Well, how would I have to do that? I would have to shift the equilibrium this way, to the left. So how could I do that? Well, increase this, it says I can't say that. Decrease this, says I can't say that. I could increase this, right? Which means increase temperature. All right, so that is one answer. I could increase temperature. What else? Well, I have gases, so let's make a box for reactants and a box for products. How many reactant molecules do I have? 2. How many product gas molecules do I have? 1. So if I wanted it to shift this way, right? I wanted to shift over here. Would I want to give it more space or less space? Well, it's the bigger number, so I'd need to give it more space. So I could increase volume, which would mean I'd have to decrease pressure. So those are the answers. Temperature is probably the easiest answer. That requires you to do less stuff, but the other ones are correct. All right, again, skip, go to the question. State in terms of the concentration of SO3 gas. So I'm going to write this down right now. SO3 gas. I got to say that in my answer, so let's just write it down right now. State in terms of the concentration of this, SO3, what occurs when more O2 gas is added to the reaction. So I add O2. Which way does the equilibrium shift? Well, here's my arrows, right? Anytime you increase the concentration of something, it shifts toward the other side. So when I increase O2, all right, then what's going to happen? The amount of SO3, the amount of heat or energy, and the things on this side will go down. So the amount of SO3 does what? Increases. All right, so the concentration of SO3 increases, and that's because the equilibrium shifts to the right. Okay? Right, so the equilibrium shifts to the right. Right? Again, excuse the mouse writing. All right, given this equation, which statement describes this system? So I see this. Again, what is this? Equilibrium. It's talking about concentrations. What do I know about things at equilibrium? The concentrations are what? Oh, there's the key word. Concentrations are what? Constant. There's my answer. Okay, long question. Skip to the answer. Not to the answer. Oh, that would be even better. But let's skip to the question. Explain in terms of collision theory. So what does that mean? Again, I must talk about collisions or collide in my answer. Why an increase in temperature increases the rate of reaction between methane gas and steam. Again, we had a question almost exactly like this. So all I have to say is an increase in temperature increases the number of collisions, and it increases the energy of the particles when they collide. So it increases the energy of the collisions as well. Okay, so of collisions. So again, my answer has to say collision, collide, right? All right, again, skip to the question. Describe one change in the HCl aqueous that will increase the rate at which hydrogen bubbles are produced when the acid is applied to a steel frame. So I'm looking at this equation right here, okay, because that's the only one that has HCl in it, right? I want to increase the rate of H2O bubbles, okay? So how could I do that based on HCl? Well, I could increase concentration of HCl, right? What else could I do? Temperature? Yep. I could also do something with gas. I only have gas on one side, so it's better to just kind of leave that out as an option. So increased concentration of HCl is key. All right, skip, go to the question. Explain in terms of reaction rate. So that means I need to say, did the reaction rate slow down? Did it speed up? Did it stay the same? So explain in terms of reaction rates why the concentrations of the reactants and products remain constant. Well, again, look at this key word right here, equilibrium. So why do the concentrations remain constant? Because the rates of the forward and the rate of the reverse reactions are what? Equal. So if the rates are equal, the concentrations remain constant. All right, which change would cause an immediate increase in the rate of the forward reaction? So forward goes this way. So how could I make the reaction go this way? So let's think about it. Before I even look at my answers, how could I make the reaction go this way? Find my arrow, okay? Everything, in order to go this way, everything on this side would have to increase, and everything on this side would have to decrease. So is it decreasing temperature? Nope. Is it increasing NO? Nope. Is it decreasing pressure? Well, I didn't look at pressure yet, but let's look at it. Let's make a box for reactants and a box for products. How many reactant gas molecules do I have? Well, I have one N2 and one O2, so 2 total molecules. How many product gas molecules do I have? 2 NOs, so 2 total. So since the number of molecules is the same on both sides, pressure does nothing. Well, this better be the right answer. Increasing N2. Oh, yep, that's what I said. Increasing N2. All right, given this equation, what change in reaction conditions will increase the frequency of effective collisions between reactant molecules? So how do I increase the number of collisions? You remember, what are those ways? I could increase temperature. Is that an option? Nope. I could increase surface area. Is that an option? Nope. Okay, I could increase pressure or decrease volume when I have gases. Is that an option? Nope. So what's the other one? Increase concentration. And there it is, right there. All right, a chemical reaction between iron atoms and oxygen can only occur if, do you remember? First of all, they got to bonk into each other. Effective collisions. All right. And given this reaction, what occurs when the concentration of H2 is increased? So I'm increasing H2. Find my arrows. So whenever I increase something, the reaction is going to shift toward the opposite side. So that means it's shifting to the right. And the amount of the NH3 will go up, the amount of N2 will go down, and then the amount of H2 will also start to go down. So I can eliminate 2 answers right away because this says shift to the left, wrong, shift to the left, wrong. So I know it shifts to the right, and what did I just show was happening to the amount of N2? It was decreasing. All right, and there we go. That's it. That's some review. Hopefully that helps.